Day, so I've got mixed feelings, some of relief and other of, I'm going to miss everybody. If you enjoy teaching, I think you always feel like, oh, I want to go back, right? So we want to complete this chapter today and also go on to the next chapter, which is distribution system reliability. I think we did almost all these studies in interconnected power systems, and we mentioned the benefits of connecting one system A to another system B via some tie lines, transmission lines or cables. And we also considered some variability, meaning we considered the variability of the tie line capacity. We changed the tie line capacity and saw how the risk in the system A changes when we have assistance from system B, right? So how we managed this was, we take system B, which is the assisting system. System A is the assisted system. So from system B, whatever maximum capacity it can provide, we build a model, a capacity model. And then we move that model through the transmission line. And initially we assumed that the transmission line was fully reliable. That means if it is a 10 megawatt line, it is always available, no failures. So then we constrained the model from B through the tie line, because the capacity from B we were able to get maximum 20 megawatt, but our tie line was only 10 megawatt. So we had to change the model, and we got the tie line constrained equivalent assisting unit model. That's a mouthful, I know, but as long as you know what I mean. So what did we do then? We came to our system A, which is the system that needed the assistance, and we added this new tie line constrained equivalent assisting unit model. We assumed that it is like another generator, and then we added it to our system A. We rebuilt the capacity model, the capacity outage probability table, and then we found the risk, loss of load expectation. So that's what we did first, and then we changed the tie line capacity, and we saw that if we increase the tie line capacity beyond 20 megawatt, it doesn't make any difference, because the maximum support that we can get from system B is restricted to 20. So therefore we shouldn't be increasing. So we saw how we change it from 5 to 10 to 15 to 20 and even beyond 20 megawatt, which of course doesn't help at all. And that's called an infinite tie capacity, right? We mentioned those words. And then we also changed the reliability of the tie line. We said, okay, we assume that it is fully reliable, but that's usually not the case. Everything fails, so this tie line must also fail. And we incorporated the tie line reliability and unreliability, and then we did the calculations all over again. And of course, we found that the risk increases in system A little bit, as expected. The benefit of these studies is that we are able to quantify, for every change that we make, we are able to quantify the new level of risk. Then we changed the number of tie lines from 1 to 2. And we said now we've got 20 megawatt capacity in the tie lines, and we also have the lambda and the mu of the tie lines. So we also tried to do that. Now the last thing that we want to talk about in this is the multi-connections of interconnected systems. That means more than 2 systems are connected together. So we looked at effect of tie capacity, looked at effect of tie reliability, and we looked at the number of tie lines changing. That's what I have been trying to summarize in the last 5 minutes. And now we look at multi-connected systems. That means so far I have considered system A, system B. B is assisting A. There is no reason why you can't do the other way around. I did mention yesterday that you should, as homework, try to find out the risk in system B when it takes assistance from system A. Is there anyone who has done this? Did anyone try to attempt that? No, you're all preparing for the test today, right? There is a test from 11:45, I understand. By the way, I didn't set the question, so I was not even told that there will be a test, otherwise I could have prepared something from Singapore itself, but so somebody else has done it, I do not know who. So blame it on him or her. Okay? Right, so I want to now consider more than 2 systems, because actually if you look at the power grids in the world, for example, in Asia or ASEAN, there's more than 2 countries that are interconnected through tie lines. It's not just 2, like Singapore and Malaysia is 1, but Malaysia could be connected to Thailand. Thailand could be connected to Myanmar. So there could be a much bigger network. And that in many ways is desirable, although we must also realize the downside of that. Because if there are too many failures in one system, it may affect your own system reliability, right? You don't want that to happen. So we need to be careful, but the most important factor before commencing this evaluation is the interconnection agreement. So my focus in the next 10, 15, 20 minutes is to try and tell you what kind of agreements can exist and how we handle those. So for example, we have 3 systems, A, B, and C. We have 3 systems, A, B, and C, and they are connected like this. Yeah, A and B are connected through tie line 1, A and C through tie line 2, and C and B through tie line 3. Just an arbitrary system, hypothetical system perhaps, could be real. And then we are looking at some possible situations. Situation 1, A is deficient, B and C are in surplus. So A needs help and they have more power. So how can A get the help? It can get directly the help from B via T1, right? That's one way. Secondly, it can get directly help from C via tie line T2, because both B and C have surplus. You could also argue that since B has surplus, maybe the tie line capacity is restricted, T1 tie line capacity is restricted, so maybe it can send power this way. It's entirely possible. Depends on the surplus in the system B, depends on the agreements between these 3 systems, right? So that's one possibility that may exist. Yeah, system A can receive assistance from system C, which is a direct assistance. And then another possibility, A and C are deficient, only B is in surplus. So this guy has more power to give to both A and C. So of course it will help A through T1 and it will help C through T3. That would be the normal mode of providing assistance. But it depends upon the interconnection agreements here. Who takes priority? I mean, B has surplus. Should it give first to A and then to C? Or should it give first to C and then to A if it has got any more surplus left, right? So that agreement is very important. A or C has total priority over the other and its deficiencies are made up before the other system is helped. That could be one possible agreement. So that's where all these agreements come to the fore, and we need to be cognizant of the fact that all these managers and planners and operators need to sit down and decide what kind of agreement should be in place. Yeah, there could be another possibility, A and C share the reserves of B. So for example, it has a reserve of 20 megawatt. It says I'm going to give 10 to A and 10 to C. Yeah. So all kinds of possibilities are there as long as the agreement is clearly specified. Now, we can actually talk about systems that have 4 or 5 subsystems connected together. So I just want to show you some possible scenarios like this. We have 4 interconnected systems here in the top 2 diagrams, and we have 5 interconnected systems in the bottom 2 diagrams. So 4 interconnected systems with indirect assistance. Indirect, you see A is assisting B, B is assisting C, C is assisting D. All indirect, right? B cannot get directly from A, D cannot get directly from B. So that may be one possible scheme. Or 4 interconnected systems in a mesh formation. So C can also assist A. So that's a new variation here as opposed to this one. C is also able to assist A. That's a possible thing. And finally, for 5 systems where the evaluated system I am considering as system E. So E is the one that we want to consider, how much help it can get from the neighboring systems. So A to B to C to D to E. It's the same sort of indirect assistance, right? And finally, another way that you want to evaluate system E, A is not going to B, but B is giving supply to A, and then A is assisting E. And also D is assisting E. So this is very good for system E. It's getting support from everywhere, right? So again, all these are possible scenarios. It all depends upon how the agreements are signed between the neighboring countries or utilities or whatever you want to call them, okay? So just to conclude this particular chapter about interconnected power systems, the determination of the benefits associated with interconnection is an important aspect of generation system planning, particularly for future capacity planning. Yeah. This chapter has presented a technique for evaluating the reliability of two or more interconnected systems, the equivalent assisting unit approach. I also mentioned that there is another method called the probability array method. So if you're keen, you can also look into that, but that's usually a little bit more clumsy as opposed to the equivalent assisting unit technique. So that's why I'm picking the method which I believe you should be able to handle more easily, and you can even program it. The concept of using an equivalent assisting unit which can be added to a single system as a multi-state unit. It could be two-state unit, the equivalent, it could be three-state, four-state, depending upon how much it can assist and how much can move through the tie line, right? So generally it is a derated state model, multi-state model. And this is a powerful tool for interconnected system studies. The equivalent model can easily include the transmission, can include any operating constraints or agreements. So that's what we have mentioned so far this morning. The numerical value of the reliability associated with a particular interconnected system will depend on the assumptions used in the analysis. All along last 4 or 5 days, we have been saying we use approximate methods, we use assumptions, right? In addition to the actual factors which influence the reliability. So we must all the time make sure that we know that there are assumptions, there are approximations in all these analyses, and there is uncertainty, right? So that, I think, concludes this chapter, and I want to now move on to distribution system reliability, CH10, if somebody can just put it on. But are there any questions that you have for me? Questions, comments, brickbats, bouquets. I can take brickbats also, although I would love to have bouquets, right? By the way, if we finish, I don't have my watch here, I took it off. If we finish this chapter before 11:30, then last night I tried to make some more slides using the example of maintenance in distribution system. So if time permits, we will look at that, but we'll have to take it out from my computer, yeah, later on. Okay, so distribution system. Now, I did say when we started with power system reliability that in general, most of the outages in a real power system from the customer's perspective happen in the distribution system, and yet most of the focus in reliability assessment has been on generating systems and transmission systems. The reason is simple, because they are highly capital intensive. You spend millions and millions and millions on those parts. Why? Because they need to be robust. You don't want outages that result in complete blackouts, right? Whereas in the distribution system, the outages are localized. I mean, maybe 100 customers, 1,000 customers will be affected. But if there is an outage in generation or transmission, maybe millions of customers may be affected, if not the entire country, right? So that is a little bit understandable, but that's what has happened. Generation has been the focus of a lot of reliability studies for the simple reason that the outages there can have serious or drastic consequences. But we must realize that many of the outages come from the distribution system, particularly from the customer's perspective. So if you look at these statistics here from a utility in the UK taken some time back, you see that 11 kV and below is almost, what, 87%? More than 87%? Yeah. My own studies, when I did during my PhD and a few years after that I continued in the same area, told me that more than 80% of outages in an electric power system come from distribution. Of course, I was using test systems. That's the difference, whereas this is a real system. So you can still see that it's more than 80%. So from customer point of view, they don't care, you know, how you reinforce the generation, how you reinforce the transmission. They are only interested in whether they can get power from the utility or not. So let's look at how we evaluate the distribution system reliability. That's going to be our focus this morning. Usually, most distribution systems are radially connected. Yeah. Now, a radial system is probably not the most reliable, but it is the most prevalent. Yeah. Truth be told, some systems are connected to a mesh or a ring. Yeah. I will talk about that as well a little bit, but to begin with, we'll start with a radial distribution system. Yeah. So it consists of a set of series components, including lines, cables, disconnects, bus bars, etc. So when components are connected in series, we have learned that lambda is equal to lambda 1 plus lambda 2 plus lambda 3, right? And then we can find the R and we can find the U, correct? If components are connected in parallel, we also have equations. We have learned all that in the failure modes and effects analysis, in the minimal cut set technique, and so on. So the three basic reliability parameters that we shall calculate in distribution systems, which are not really any different from what we do in generation systems, are the average failure rate, average outage time, and average annual outage time, also known as unavailability. That's why we use U. U stands for unavailability. So unavailability is the annual outage time. R is the average time, whereas this is in hours per year. This is in hours, right? So that's the difference between the two. And lambda is in failures per year or failures per period, depending upon the length of the study. So these are the equations that come to the fore if the components are connected in series. And I just mentioned that for a radial system, more often than not, you have all these components connected in series until you get the power. So if any one of them fails, you lose power, right? So this is how we'll calculate the average failure rate, average annual outage time, and average outage duration. So let's consider this radial feeder. There is power coming at this bus, yeah, and this is a circuit breaker. This is a section A, another circuit breaker, section B, another circuit breaker, section C. And we have got these loads L1, L2, L3 connected at each of these buses, right? Very simple. Every power engineer can relate to that very easily. It's a 3 load point radial feeder, okay? So the assumed failure rates and repair times are shown here. So we have these lines A, B, and C. The failure rates are 0.2, 0.1, 0.15, and whenever they fail, then the outage duration or the repair time is 6, 5, and 8 hours respectively. Yeah. Once again, let me show you the diagram. We are given the failure rate of this section. We are given the repair time of this section. Same for section B, same for section C. Now let's see the operation of this. The customers are connected here, here, and here. What are we interested in? We are interested in finding the reliability of supply here, here, and here, right? That's what we are interested in. So suppose there is a failure of section A. Suppose there is a failure of section A, means a single phase fault, double line fault, or 3-phase fault. We are going to assume that for any fault, all the 3 phases trip, yeah, for simplicity. So what will happen? This breaker will trip, right? Correct? And you have to repair the fault before you reclose the breaker, correct? So therefore, this load point will be out. It will not get power for the 6 hours or 8 hours that you are repairing this component, right? So that's 6 hours. Yeah, that's 6 hours, right? In this, for the, I think this thing is getting unreliable. Not sure if it is a battery problem or is it me. Okay, now let's hope it will continue. So now load point 1, I was talking about there is a fault here, then you need to repair, right? So load point 1 is out for 6 hours. It will not get power for 6 hours, correct? And how is it affected by failure rate? The failure rate is the same as the failure rate of component A, right? And the outage time is 6 hours. Therefore, the unavailability is 6 times the failure rate, correct? Now, let's talk about the failure of section B. If this fails, this breaker will trip and it will not affect the load point 1, correct? That means load point 1 can continue to be served. If there is a failure of component C, it will not affect load point 1, clear? So, load point 1 is impacted only by failures of component A. Load point 2 is impacted by failures in component A and B, correct? And load point C, poor guy, is affected whenever there is a failure in A or B or C. So, the customers that are farthest away from the supply are the worst off, yeah? That's how the radial system works, because everything is in series, like we said, okay? So, if we look at the, oh yeah, come on, another 1 hour, just stay with me for another hour, yeah? So, the load point reliability indices for L1, as I said, 0.2 failure rate for section A multiplied by 6 hours, the repair time of section A. So, the unavailability is lambda times R. For L2, you have to add lambda 1 plus lambda A plus lambda B, yeah, that will be the effective failure rate, and then the unavailability is, let's go back there, unfortunately, this is giving me trouble. Maybe we need to look at it. Probably a battery problem, but reliability, unreliability can come from anywhere. Thank you. So, for load point L2, what will it be? It will be 0.2 times 6 plus 0.1 times 5, right? The unavailability. So, that's the number that you see here, 1.7. So, 1.7 divided by 0.3 will give you the average outage time. Similarly, for load point 3, which is the worst, as you can see, failure rate is the worst, total unavailability is the worst, as is the outage time. Okay. So, in general, when we deal with distribution systems, and some of you may be experts in power quality, and you may have heard of indices like SAFE and SAIDI. Have you? Anybody in power quality area? You have heard about those, right? Yeah. Yeah. SAFE and SAIDI are two of the most popular indices used in power quality as well. So, even in reliability of distribution systems, we use additional interruption indices. Not just the indices of lambda, R and U, but we also want to calculate additional indices. Why? Because you know the failure rate of load point 1, but does it tell you how many customers are affected? It could be one customer, it could be 1,000 customers, it could be 10,000 customers. Does it tell you how much load is interrupted? 1 kilowatt, 1 megawatt? It doesn't, right? So that's why we need these additional indices, which will give us more information about the performance of the system. So, those additional indices are defined here. There are two types. One is called as customer oriented indices and the other is called as load oriented indices. The customer oriented indices are generally more common as opposed to the load oriented indices, but I've given you the equations here for all the indices that can be calculated and are frequently calculated. SAFE is the total number of customer interruptions divided by total number of customers served. Yeah. So now this is for the system, for the entire feeder. When I showed you the indices of lambda, R and mu, these are for individual load points, L1, L2, L3. Now I'm saying I want to find the reliability of this entire system. Yeah. Not just for L1, not just for L2, not just for L3. That's where we come to customer oriented indices. So, total number of customer interruptions, which is lambda times n, where n is the number of customers at load point I, okay, divided by the total number of customers in the system, in the feeder. Okay? That will give you SAFE. And then the other more popular one is called SAIDI, System Average Interruption Duration Index. Interruption duration, this one is interruption frequency, right? So this gives you the frequency, this gives you the duration. Remember, we have been saying from a customer's perspective, frequency and duration are much more meaningful, right? So here we are. Sum of customer interruption durations. This one is duration, this one is frequency. Remember, we also said that frequency is equal to lambda. We made that approximation somewhere along the line, right? So UI and I divided by summation. There is another one called KFI, total number of customer interruptions divided by total number of customers affected. Not the total number of customers, but only those that are affected by those interruptions. KD is defined like this, which is nothing but SAIDI over SAFE. Yeah, if you look at this, UI NI over lambda I and I, because the denominator will get cancelled, right? So KD is SAIDI divided by SAFE. Yeah, that's another way of calculating KD. Okay, and then we have average service availability index and average service unavailability index, which is obviously the complement of the availability index. And those are the equations that are used to calculate those, where the total number of hours in a year is 8760. So these are the main customer oriented indices. Then we have the load and energy oriented indices. So average load is LA, peak load is LP, yeah, and LA is defined by this particular equation. Then the energy not supplied in this total feeder, total system, subsystem, or whatever you are interested in, is the average load multiplied by unavailability at each load point. And if you sum it up, you will get the energy. I mean, what's energy? It's power times hours, right? Megawatt hours. It's somehow you have to combine the power and the duration. That's what we are doing. This is the average power, this is the unavailability. Okay? And average energy not supplied, you divide it by the total number of customers. That will give you the average value. Okay? So these are some of the indices well documented in the literature. Depending upon your application, you may or may not calculate them. But two things very clearly here: individual load point indices and system indices. These are system indices. Customer oriented indices are for the entire feeder or for the entire system under consideration, which may comprise hundreds of load points. The example we have used here is only 3 load points, okay? So now, before we look at some cases of how we calculate the reliability and unreliability, yeah, I just want to tell you that these customer-oriented and load-oriented indices are very useful for assessing the impact and the severity of outages in a distribution system. And as luck would have it, most of the utilities do these calculations at the present time more widely used for the current system to assess the they are more widely used in this respect than as a measure of future. In other words, you have your system, you have the failure rate, you have the outage time of the lines and of the bus bars and breakers, and then you want to calculate the performance of the system based on historical data. But you can also do it for a measure of future performance, right? So why it is being done based on the current system is it establishes the chronological changes in system performance and therefore helps to identify weak areas. You want to do it so that you know, oh, which part of the system is more prone to failures, so I can put more reinforcement there. It establishes existing indices that serve as a guide for acceptable values for future systems. If you don't have anything to go by, how will you plan the reliability in the future? So at least now you have a guide. You say, okay, this is the reliability of my system. Do I want to enhance it? Do I want to keep it that way? Or can I allow it to degrade? At least you have a general guide. And last but not least, it enables previous predictions to be compared with the actual operating experience. You already have your system, you know how it was behaving in the past, and you can now compare it with what happens in the future. Okay? So those are some of the ways in which these reliability calculations can help. So now let's apply it to a radial system. Like we said, many distribution systems are connected radially, and the techniques that we are describing here are used to evaluate the three primary indices. What are those three primary indices? Something has gone wrong. I thought it was working now. No, go ahead, go ahead. Thank you. Where was I? Yep. So we are going to apply it to a radial system. So let's look at this system now. It's radially connected. This is where the power is coming in. This is the bus bar. We're going to assume that the bus bar is 100% reliable. The reason is simple. If this bus bar is to be maintained, you cannot get power anywhere, right? So normally a series component like a bus bar is not maintained unless you have another connection point. Yeah, that means you connect it in the form of a mesh and then you maintain this bus bar. So right now we are not considering that. Very soon we'll move towards that. So this is a typical radial distribution system. Now you see there is only one breaker here. Yeah. So this is a single line representation of the system, and we are going to assume that any fault, single phase or otherwise, will trip all the three phases. Okay. So keep it simple, otherwise it is even more complex. You have to bring in the concepts of fault analysis, protection, right? So the basic data of this system are shown here. We have got four main sections, 1, 2, 3, 4, and we have got four distributors, A, B, C, D. Yeah, this is called a distributor, the lateral. You can call it a lateral section or a distributor, A, B, C, D, and these are the main sections. They are all cables or transmission lines. Okay. And this is where our loads are connected, capital A, capital B, capital C, capital D, okay? Only one breaker. This is the system that I have chosen right now, okay? And these are the data. So all the four main component sections, they take a repair time of 4 hours. All the four lateral distributors, if they need to be repaired, they can be repaired in 2 hours, okay? Again, keeping the data quite simple. If all component failures are short circuits, then each failure will cause the main breaker to operate, isn't it? I mean, if there is a fault here, operate, fault here, operate, fault here, operate, fault here, operate, isn't it? Now, this is one of the most unreliable systems. There is only one breaker, and what do you expect the reliability for these four load points? Do you think any of them is better than the others? Just look at this system. Even before we look at the numbers, because any failure 1, 2, 3, 4 impacts all the four. Any failure A, B, C, D impacts all the four. Therefore, you would expect the reliability of all the four load points to be the same, exactly the same. Yeah. So, okay, so I'll show you this table first. The reliability is exactly the same. Okay, we'll go back to the SAFE SAIDI in a while. So you see section 1 out, the failure rate is 0.2. Whenever it fails, you need to repair it. The repair time is 4 hours. Therefore, the unavailability is 4 times 0.2. Clear? Whenever section 2 fails, also repair. Section 3 fails, repair. Section 4 fails, repair. Correct? And then lateral distributor fails, repair, everything is the same. You see the reliability of load point A, load point B, load point C, load point D, exactly the same. It's a highly unreliable system and probably not the best system to have in any radial distribution circuit. So I have this data here as well. Why? Because we also want to calculate the customer-oriented indices and if possible, the load-oriented and energy-oriented indices. So the data is given for all the load points A, B, C, D. the number of customers connected at each of those, and the average load connected at each of those 4 load points. So you can calculate the SAFE, SADI, KD, SUI, SI, ENS and AENS according to the equation that I showed you earlier. Yeah. Calculations are quite straightforward. Remember the SAFE equation? Yeah, you just need to know the equation. Yeah, so lambda I times Ni over summation of lambda I. So what will you do? Lambda, yeah, lambda of load point 1, load point A in this case we are calling, multiplied by number of customers at load point A, plus lambda B NB plus lambda C NC plus lambda D ND, divided by total number of customers. And the total number of customers you can get from here. You can get from here. Total number of 700 plus 500. So you can actually calculate these numbers very easily. That's why I did not show those calculations, because they are directly coming from those equations that we highlighted earlier. Okay? Note the units. SAFE is an interruption frequency index. So it is interruptions per customer year. Yeah? It's an interruption, it's a frequency index. SADI is a duration index. So it is hours per customer year. SAFE is interruptions per customer year, SADI is hours per customer year. And KD is SADI over SAFE, yeah? SADI over SAFE, as I mentioned earlier. And then of course the availability index, the unavailability index, you can see that the system is reasonably reliable, 0.999315. And the energy not supplied using the equation, because we have the average loads, if you remember. How do we calculate the energy not supplied? Yeah, we have the energy not supplied is average load multiplied by the unavailability. And we have the unavailability at each of the 4 load points. We have the average load at each of the 4 load points. Just sum them up, and then AENS just divided by the total number of customers. These calculations are straightforward. I have not shown them in the slides because they are relatively easy. Yes, ma'am. Yeah.
The lambda is of both section and...
No, it's the load point. Now we are at the load point. Because this is a system customer oriented index, not the individual section. It's the load point.
For the distributor.
At the load point. So in other words, it's this one. Lambda 1, lambda A multiplied by number of customers at A, plus lambda B multiplied by number of customers at B, okay? Right, so we have seen a very simple configuration, only one breaker. Whenever there is a fault on any main section or lateral distributor, the breaker operates, and therefore we lose power at all the load points. Not the best system to have. So now we are going to consider lateral distributor protection. In other words, all these laterals that you saw, the distributors that I call, I'm going to install fuses in each of those, so that whenever there is a fault in this lateral, if there is a fault, the fuse will blow, and it will not affect the other load points. It will only affect the load point where the lateral is connected. Of course, when the fuse blows, you have to rectify the fault before you connect another fuse and you close the circuit for that load point. But it will not affect the other load points, correct? So that's what we have shown here with lateral protection. You see, for the main section, no change. Whenever there is a fault in the main section, the breaker will operate and you can't get any supply, right? But for the distributor, previously we had all the 4 entries, but now we don't. Why? Because its own lateral, if the fuse blows, there is a fault, you have to repair it. But if the lateral B, there is a fault, fuse blows, it does not affect load point A. Lateral C does not affect load point A. Lateral D does not affect load point A, correct? Then you come to load point B. Yeah? For the main section, no change. For distributor A, if there is a fault, the fuse will blow, and therefore it will not affect load point B. It will not affect load point C. It will not affect load point D. So there is only one thing that will affect from the distributor side, that is its own distributor. Load point A's distributor or load point B's distributor, yeah, because its own fuse will blow. You have to repair the distributor before you put another fuse and close the circuit, okay? So this is obviously more reliable, right, compared to the previous configuration. So what do you see now? Failure rate is only 1.4, 1.2, 1, and the unavailability is 3.6, 4, 4.4. Now if you compare this, just try to remember 1, 1.4, 1.21. Just try to remember, because I need to keep going back and forth. I have no choice. So you see here 2.2, 2.2, 2.2, 2.2. All of them were equally reliable, or shall I say equally unreliable. But now we have improved, right? 1, 1.4, correct? So the failure rate has gone down, which is good. What do we want at the end of the day? Failure rate should go down and unavailability should go down, because the repair time R is U over lambda. So that's a ratio of two quantities. We can't control that. If we can control lambda and U, then, R will subsequently also reduce. Clear? So that's the lateral distributor. I connected some protection in the laterals and the reliability has improved. And of course you can calculate the additional indices. You will find that they have also improved. Now we do something else now. That system is also not as reliable. So we are considering something else now, and I'm going to show you the drawing first. There is a breaker as before. There are fuses in each of the laterals. In addition, I have put this disconnect. I call it a disconnect. It's just a switch, yeah, which can be opened or closed. It's not a fault breaking switch, meaning it's not a breaker. You have to do it manually, okay? So we are calling it a disconnect. So there is one disconnect at the beginning of section 2, one at the beginning of section 3, one at the beginning of section 4. I don't need at the beginning of section 1 because there is a breaker over there, okay? So we are slowly enhancing the system in the hope that the reliability will improve. And of course it should. By how much? That's where reliability evaluation techniques come into play. So what will happen in this system now? If there is a fault in section 1, the breaker will operate. The load point A is out, right? Load point B is out, load point C is out, load point D is out. So main section still the same. But what happens if there is a fault in section 2? What happens if there is a fault in section 2? Well, you can use this disconnect. The breaker will go off, of course, but while things are off, you can open this disconnect and then close the breaker so that there can be power to load point A. Are you with me? So any fault here, now I don't need to repair number 2 for load point A. I don't need to repair. I only need switching action. I need to switch the disconnect on and off. And that switching time is usually much less compared to the repair time of the component. So I have used a switching time of 0.5 hours as opposed to the repair time of this section, which was 4 hours according to our data. Clear? Similarly, if there is a fault here, I can again, the breaker will go off, then I use this disconnect, I open it up, and then I close the breaker. So load point A, load point B are now supplied. Only load point C and D are disconnected. Clear? Similarly for fault in section 4, only load point D is impacted. The other 3 can be recovered after the switching time of 0.5 hours. Clear? So we see that this situation is also very nice. So section 1 out, you have to repair, no choice. For load point A, okay, just look this way, one at a time, right? Load point A. So section 1 out, no choice, you have to repair. Section 2 out, as I mentioned, the breaker will go off, use the disconnect, and then turn the breaker on. So you only need switching action. You don't need 4 hours. You only need switching time. Same for section 3, same for section 4. Then when it comes to lateral, there is a fuse there already. So only its own lateral needs to be repaired. The others won't contribute at all, correct? Just like the previous table, okay? So let's come to load point B. Load point B, first section failure, you need to repair. Second section failure, you need to repair, right? If you're still not sure, let's go back here. Now we are looking at load point B. If there is a fault on section 1, breaker goes off. You have to repair section 1, right? No choice. If there is a fault on section 2, breaker goes off. you can't open this because you still cannot supply load point B. So you have to repair section 2, correct? But when you come to load point C, you can isolate from here if there is a fault on 2 or fault on 1 and then reclose the breaker, right? So A and B can be supplied if there is a fault here, if there is a fault here, and so on and so forth. So that's how we arrive at this. You see, the lateral distributor, only one entry, and for the main sections, for B, only the first 2 components will need repair, the other 2 can be switched. Yeah, for load point C, first 3 components need to be repaired, the 4th can be switched. The last load, nothing, it doesn't help anything, yeah, because there is only one breaker and you can't connect the load from other sources. Again, you can calculate the SAFE, SADI, KD, and ASI, ASUI, ENS, and AENS, etc. Okay. Now, we have done a few cases. We have seen the impact of protection failures. We have seen the impact of disconnects. But let's go back to this protection failure. There is a fuse there in the distributor. Who's to say whether the fuse will operate whenever it is called upon to operate? You tell the fuse, hey, it's time for you to kick off, yeah, because there is a fault, and it refuses to operate. So it has its own reliability, right? So we are going to consider that now, okay? That's why this thing can be very interesting. You can include almost everything under the sun. Okay, so occasionally the primary protection system fails to operate. So what's the primary protection for the load? It's the fuse, right? That's the primary. The breaker is the secondary protection. So occasionally the fuse refuses to operate, and then you have to go back to the backup protection. So we are assuming now that the fuse gear operates with a probability of 0.9. We are assuming. Of course, it should be quite reliable. If you say that the fuse operates with a probability of 0.1, then what the heck? Might as well not have it. The other 0.1 is so bad, right? So usually it is expected to have a high reliability. So I'm using 0.9. That means the fuse operates 9 times out of 10. Okay? I mean, in simple layman terms. So in this case, the reliability indices can be modified, and let's look at that. We need to find the effective failure rate using the concept of expectation. I've been using that word for the last 3-4 days. Expectation, mean, average, right? So we say, what is the failure rate if the fuse operates? Multiplied by the probability that the fuse operates, right? Conditional probability. Okay, so failure rate when the fuse operates is 0. If the fuse is operating, then there is no failure, right? Multiplied by the probability of fuse operates, that's 0.9. And the failure rate when the fuse fails, multiplied by the probability of fuse fails. Probability of fuse failure is 0.1. Failure rate given that the fuse fails, the contribution to load point A by distributor B. So let's go back to the data of distributor B. Yeah, distributor B, you see here, the failure rate is 0.6. So that particular distributor has a fuse, and now because the fuse may not operate whenever it is called upon to operate, this lambda needs to be modified. The failure rate is no longer 0.6. Yeah, it becomes different. So that's what we have done using this conditional probability. Yeah, so 0.6 times the probability that the fuse fails. So we get 0.06. So now let's look at the reliability of each of the load points. So what happens when section 1 fails? Of course, you need to repair it. When section 2 fails, you can switch, yeah, using the disconnect. Okay, 3, 4, this one is the same, no impact. Then we come to the distributors. For load point A, I'm only going this way now, okay? Just focus on this side. So distributor A fails, you got to repair it, no choice, okay? Distributor B fails, now you can switch it, right? Where is our system? Yeah. So distributor B, there is a fault, yeah? The fuse will fail, and the fuse is there, and therefore the load point A is not affected, right? In fact, you can switch, right? There is a disconnect here. So even if this fuse fails to operate, yeah, you can use the disconnect. So you will see that it is only the switching time. Yeah, it's only the switching time, 0.5. Same for lateral C, same for lateral D. Then for load point B, first section, repair. Second section, repair. Third section, you can switch, right? Because there is a disconnect. Fourth section, you can switch because there is a disconnect. Then the laterals. Lateral A, you can disconnect, 0.5 switching, but the lateral B itself, which is feeding the load, you have to repair. And then the others will also be switched, okay? So this is how we incorporate, but you should notice the lambda here. That's the one to notice, 0.06. Here. Given that the fuse may fail, right, you need to use the modified failure rate. So we didn't use the original failure rate, we used the modified failure rate, 0.06, 0.04, 0.02, okay? So that's how we will calculate the reliability indices for each of the 4 load points, A, B, C, D. If you now compare the reliability of each of these 4 load points, just try to remember, let's say, load point 1, 1.12, 1.56, just try to remember that. It's worse off, right? Yeah. So the reliability has deteriorated. You would expect that because the fuse is operating only 9 times out of 10, not 10 times out of 10. So you can see the impact numerically, analytically, how it impacts the numbers. Okay. So reliability indices, you can also calculate the customer-oriented indices as well. Okay. Now the last one, we haven't yet considered any supply from the other side. We say only supply is coming from here and then the radial feeder is going like this. Now suppose at the end of this radial feeder, I have a normally open point, NO, normally open point, and there is something else here, either in the form of a mesh or a ring or whatever, which I can use as a backfeed. Meaning in the hour of need, if I close this switch, I can get power back here. Yeah, as long as I don't create a fault while doing so, correct? So you have to do it carefully, of course. So this changes the paradigm completely because now I have got another source of power and we can expect the reliability to improve, correct? So this is what we are after now. Transfer restrictions. We want to see how the transfer takes place. Yeah, here, no restrictions on transfer first, and then we will assume some restrictions on transfer. So this point, normally open point, it will supply power whenever you want it to supply power, no restriction. That's the first case I'm talking about. Then we'll see how the restriction case happens. So in this case, the reliability index of each load point is shown in the table, and this indicates that the failure rate of each load point does not change. The failure rate of the load points does not change, but the indices of load point A do not change because load transfer cannot recover any load, right? So even if I get power from here, suppose there is a failure in section 1. Suppose there is a failure in section 1, this breaker will go off. Can I provide power from here to load point A? I cannot, right? Because there is a fault in this section. The minute I try to provide power through this, then again the fault will be there, right? I'm reconnecting the fault. So load point A cannot benefit from this normally open point, the backfeed, the alternative power supply. But all the other load points will benefit. For example, load point B, if there is a fault in section 1, the breaker goes off, you use this disconnect, open it, connect this normally open point, close it, and then you get the power to B. You get the power to C, you get the power to D, correct? So in this case, as you can appreciate, the load point D stands to benefit the most. In the previous case, when this is not there, this is the worst, and now it is the best. Why? Because right next to it, there is another source of power. So this is how we can quantify. Where is the table? Yeah, it's right here. So load point A, section 1 fails, you got to repair it. Section 2, 3, 4 fail, you can connect the alternate supply just by opening this, keep this breaker open, and then you can feed the power to the load point B, C, and D, right? So each of these you can feed. Section 1, repair. Section 2, switch. Section 2, you can switch off, right? Section 3, you can switch off. Section 4, you can switch off, 0.5 hours. For load point B, section 1, you can switch. If there is a fault here, the breaker will go off. Now, you use this disconnect, open it, and then you close this, and you can feed load point B, right? So, the outage time is only 0.5. But when there is a fault here itself, then of course you've got to repair it. Then the fault in section 2, you got to repair it. Fault in section 3, the breaker will go off, you open this disconnect, you connect the power from here, so it's only the switching action, correct?
Yes, sir, but it is supposed to do that reduce the movement outage. You can put the bus stop on it.
Yeah, there's... Correct. So it depends upon your configuration and how much you want to improve the reliability, but still many systems continue to be radial. Why? You can always ask that question, why? Because nobody thinks of distribution system as critical. That's the reason. Otherwise, they should not be connected radially. Radial configuration is not good for the customers.
Regarding the protection device coordination, that global at point 1, if that gets fault, then whole system will be blackout.
No, if there is a fault here, this breaker will trip, right?
Yeah, breaker will trip, but supply will be disrupted.
Yeah, supply is disrupted here, yes.
And next you have told me we will put the various changes so that you can coordinate further.
Yeah, so we are feeding it from here.
Yeah.
We are feeding it from here.
Got the application.
Yeah.
That's why it's called one is the global blackout. Like application in the where the storage area is clear and arm ammunition there. Here demand is in a network. If anywhere fault comes, global breakers will operate.
Right.
Main breaker. So there is a possibility of somewhere it gets fault electrically originated energy that may get explosion. Damage will be much more.
Right.
In the process, industry and all these things, they have to be coordination.
Right. Yeah. I mean, you're talking about protection coordination. Yes, that's correct. Right. Yeah. I mean, like I said, most radial systems are connected like that. So there is a way for us to calculate the reliabilities of these systems. Also for the ring systems, which hopefully we'll find time. I don't know what the time is like. Do we have time for that? 11:18. I'm supposed to finish by 11:30. There is tea after that and then exam. The dreaded exam, right? So where was I? Yeah, the last case is transfer restrictions. So just now I assumed that whenever I needed to close the normally open point, I was able to without any restriction, and I could get the power from the other side. But suppose the power from the other side is not there whenever you need it. Maybe they are feeding their own feeder, maybe they have limited capacity, maybe they have a fault in their own system and they're not able to. So you will never close that normally open point. So we now consider the restriction. There is a probability that we may be able to supply power from this normally open point, and that is not 1.0. That's what we say, that there is a restriction on the transfer. So in that case, the outage time is no longer the outage time with 100% probability of transfer. It's outage time given the transfer times probability of transfer plus outage time given no transfer times probability of no transfer. Yeah, again conditional probability approach. So as an example, consider the outage time of load point B. Load point B of figure 10.4. Where is that figure? Yeah. Consider the outage time of load point B, okay? So that's the example I'm using here, just focus on that. Due to the failure of feeder section 1, if the probability of successful transfer of load is only 0.6. So outage time given transfer. Outage time if there is transfer is only the switching time, right? multiplied by the probability of successful transfer, 0.6, plus this should be 4.0, please note, this should be 4.0, probability, well, outage time given no transfer, yeah. If there is no transfer, then it will be out for 4 hours, isn't it? Because you are repairing the main section. So it's not 0.4, it is 4.0. This number is correct, but the decimal got changed. It should be 4.0 times the probability of no transfer, which is 0.4. So it is now 1.9 hours the outage time. And we need to consider that when we calculate the reliabilities. So this is how it works out with restricted load transfer. Section 1 for load point A. For load point A, section 1 you need to repair. Sections 2, 3, 4 you can switch. Distributor A, no impact. So load point A, no change whatsoever. Load point B, the main section 1, you use this outage time now, 1.9, not 4.0. Because there is a possibility of transfer, even though it is restricted. Yeah, there is a possibility of transfer. Remember in the previous case, this number was 0.5 when the transfer was 100% available. But now we have a only 0.6 probability of transfer. That's why the outage duration is 1.9. Okay, and then of course the rest remains the same. Same thing here for load point C. The first two segments will be 1.9, 1.9. Yeah, and for load point D, the first 3 segments will be 1.9 each. The lateral distributor is not affected at all by this transfer of power. It's only impacting the main sections, isn't it? Yeah, because the laterals are protected by the fuse. If you want to consider the fuse probability also, then that is another element. So I'm considering one by one, not everything together, just to show you the impact of each one of those variables. Okay. I think this is the last slide for this session. You can calculate the reliability indices. If you give me another 15 minutes, then I have another set of slides, but if not, then we can stop here. It's entirely up to you. They are driven, sir. What can I do? Exactly. Does somebody have a thumb drive? Is it this one?
Yes. Just give me.
So just want to copy this additional, this one.
This one.
Yeah.
This one. Additional.
Yeah.
Chapter 10.
Yeah.
Okay.
नहीं, एक तो PDF है, आप PowerPoint वाला ही काफ़ी है. हो गया होगा कॉपी तो, वो तो इंटरनेट वाली इशू है. Driven, I try to think of how to maximize this. So last night I said to myself, we have some time, so why don't we try to enhance the learning a little bit? Oh, you have to change the laptop. Turning out more troublesome. Thank you. Sorry about the delay. I know that I'm standing between you and the tea break, and perhaps more importantly, between you and the exam. We like to tease students whenever it comes to exams, so I'm just doing that, okay? I'm sorry the lady here has gone back to fetch her laptop, so she's going to miss a few minutes, but maybe you can tell her later on, okay? So we have so far talked about radial systems. I thought I also show you a little bit about how we deal with meshed systems and ring systems, yeah? So we have described the basic techniques for reliability of distribution techniques to simple radial networks. And these techniques have been used for a very, very long time, but they are restricted in their application because you can't apply it to meshed networks or ring networks. So now we want to study techniques which we can use for ring networks, which are very useful to system planners and operators. So I just go through very quickly. So the first one, we can use state space diagrams, yeah, Markov models if you like, yeah, which we did not study in detail, but easy to see from this particular example. So for example, I've got a ring network like this. There is power here and there is output being taken here, and there are two feeders, there are breakers 7, 8, 9, 10, there are two bus bars number 5 and 6, and there are two transmission lines number 1 and 2, two transformers number 3 and 4. Quite a practical ring network, so to speak, dual transformer feeder as we call it. So in order to illustrate the development and complexity of state space diagrams, consider this feeder and see what it looks like in a state space diagram. If you consider the total states, now let's go back. I'm considering this bus bar 5 and bus bar 6 to be fully reliable. Reason is simple. If there is a failure of bus bar 5, everything fails, right? So it is a first order failure. If you remember the minimal cut set technique, it's a first order failure. Similarly, bus bar 6 is a first order failure. So you can maintain them, and you need to make sure that when you maintain the bus bars 5 or 6, that you inform your customers and that you shut down, giving them a certain notice. That's fine. That will be called a maintenance outage, not a forced outage. Clear? We are dealing with forced outages, random outages in this particular course. So assume 5 and 6 to be fully reliable. Assume these breakers also to be fully reliable. So in this analysis, I'm considering only 4 components, 1 and 2 and 3 and 4, okay? So if each one of these components can exist in 2 states, up or down, then how many states will I have? For one component, it is 2 to the power 1. For 2 components, 2 to the power 2. For 4 components, 2 to the power 4. 16 states. So you see those 16 states in this lovely diagram. Can you identify state number 16? State number 16? Here, 1 down, 2 down, 3 down, 4 down. State number 16. State number 1, 1 up, 2 up, 3 up, 4 up, right? And then of course there are all the other states where there's either 1 component down or 2 down or 3 down, correct? That's what it is, isn't it? So this is a complete enumeration. We call it a state space diagram. Can become unwieldy if assuming 100 components, 2 to the power 100, it's impossible to use state space diagrams. That's why we always rely on approximate techniques, right? So we talk about approximate methods to calculate such a feeder. So we already know that if 2 components are in parallel, then the lambda, r and u are given by these equations. We have learned this maybe 2 days ago or something like this. Now what we didn't talk then was this PP. Can anybody tell me what this PP stands for? Lambda subscript PP. Any guesses? Remember, we are talking about forced outages, random outages. So the subscript P here I'm using for permanent. Yeah, it's a permanent outage, overlapping a permanent outage. 2 outages are overlapping one another. So what usually happens is this. For example, if I go back to this diagram, if this component 1 goes out, assume that component 1 is forced out of service, then the power can still go from here, right? Correct? So while you are trying to repair component 1, two fails or 4 fails, then what happens? No power, right? So this event where one has failed and another component fails is called an overlapping outage. They didn't happen at the same time, but there is an overlap, right? So we call it a overlapping forced outage. And we use the subscript P to say permanent outage. Very soon I'm going to show you another subscript called M, where M is the maintenance outage. We also have some transient failures in power systems. So we can use the subscript T. So you will see lambda PT. That means a permanent outage overlapping a transient outage. Lambda PM, a permanent outage overlapping a maintenance outage, and things like that. So what I'm going to consider in this approximate technique is this. Components 1 and 3 are in series. Very good. Components 2 and 4 are in series. So I'm going to use series concepts to find the lambda, R and U of this, and the same for this. And then this one is in parallel with this one. Series parallel concepts, right? So that's the approximate method that we are using here. And for 2 components in parallel, we use these equations, okay? And of course, if there are 3 components in parallel, we also know the equations. So the network reduction method says you combine the components in series where possible and in parallel, and then you calculate the reliability. Of course, this method can only be used provided components are connected in series or parallel. Otherwise, we should use the minimal cut set method, which we now hopefully love very much. Or I believe that you do, right? I always do, but I hope that you do too. So in this case, network reduction, 1 and 3 are in series. Yeah, let's go back again. 1 and 3 are in series, right? So what's the effective failure rate of this? Lambda 1 plus lambda 3, series, correct? Similarly, 2 and 4 are in series. So that's what I have done. I have calculated the lambda 1, 3 by adding the 2 failure rates and then unavailability accordingly. Similarly, then the 2 elements are in parallel. 1, 3 and 2, 4 are in parallel. So total permanent overlapping permanent, lambda PP. The first feeder overlapping a failure in the second feeder, and you can use the parallel equation for 2 components in parallel, and you will get the lambda, R and U. So the main disadvantage, as I said, is that components must be in series or parallel. But this is just to illustrate that there is a method which can be used. But the one that we generally will use is failure modes and effects analysis. So this is the reliability data for our system. Component 1, 2, 3, 4, the failures per year, and the outage time. Whenever the component fails, then how long does it take to repair? Remember, 1 is a feeder, 2 is a feeder, 3 is a transformer, 4 is a transformer, right? Yeah. So you can see that the transformer outage time is much higher. That we also mentioned that yesterday. Usually when a transformer fails, it takes much longer to repair. Sometimes, weeks, if not days. So failure modes and effects analysis. Do you remember the minimal cut set technique? What does the minimal cut set technique say? That the elements of a cut set, all of them must fail in order for the system to fail. And the system can fail if any cut set fails, right? So the cut sets are in series. The elements of the cut set are in parallel. I hope that you still remember. A test is coming up very soon, right? So that's what we are going to use. So we go back to that system and we see what are the overlapping failures. Yeah. What are the ways in which the system can fail? Minimal cut sets. Let's go back to that circuit. So what are the minimal cut sets? 1 and 2, 1 and 4. 3 and 2, 3 and 4, correct? Yeah, so that's exactly what you see in this table here. Yeah, 1 and 2, 1 and 4, 2 and 3, 3 and 4. And using the equations for 2 components in parallel. The elements or components of a cut set are in parallel, right? And then all the cut sets are in series. So I can add this to get the total lambda, clear? and I can add this to get the total U, and the total R is total U divided by total lambda. That's how you get this number. Okay, so it can be done. Two outages, permanent outages we call them, forced outages, overlapping one another. Please remember overlapping, they're not happening at the same time. If events happen at the same time, it's called a common cause failure. For example, if there is a fire in a generating station, then all the generators can go out at the same time, right? That's a common mode failure or common cause failure. Must be treated separately. Right, and finally I have this inclusion of scheduled maintenance, as I promised. We also spoke about it a little bit yesterday, how we can include maintenance in the reliability evaluation of generating systems. Now we see how it can be done for distribution systems. So a scheduled maintenance outage is one that is planned in advance, we know that, and can be deferred if necessary. Can be deferred. I mean, maybe you have planned it to happen from March 8 to 10, and yet you see that your system is now vulnerable. You say, no, I can't do the maintenance now. I will defer by a week or 10 days, right? So it should be deferable. It should not be like cast in stone, as we say, and involves the removal of a component or components in order to perform preventive maintenance. So when we say maintenance, we use two words, preventive maintenance and corrective maintenance. Corrective maintenance is repair. Preventive maintenance is to keep everything in good state so that it continues to perform very well. So right now we are talking about preventive maintenance, right? Not corrective maintenance. That's the repair. We already know the repair process. So a scheduled outage is not usually included in the reliability evaluation if by that action alone the load point is disconnected. So I gave you the example just now in the circuit. I said bus bar 5 and bus bar 6. They are first order failures. So I will not perform scheduled maintenance on those bus bars because by that action alone, I'm disconnecting the load, right? So that's something that we need to be very aware of. Consequently, scheduled maintenance of radial systems or of single series components, example bus bar 6, are not considered, yeah? Of course, this does not mean that we'll never maintain them, but as long as you inform the customers in advance and things like that, okay? So how do we evaluate? Let lambda I double prime and R I double prime be the maintenance outage rate and maintenance time of component I. Okay, of course it's mathematical. I can't run away from mathematics. I try to keep it very simple. So I'm going to perform maintenance on a component I. I will need to know what is the rate at which I maintain component I, and whenever I maintain component I, how long do I take to maintain component I, isn't it? So that's lambda I double prime and R I double prime, okay? And lambda J and Rj are the forced outage failure rate and repair rate of component J. Now this is the normal failure rate and repair time that we are used to. All this while we have been saying, oh, what is the failure rate? What is the repair time, right? So those are the normal ones that we are familiar with. And now we introduce another one, lambda PM, RPM and UPM. So what is lambda PM? It's the failure rate of a permanent outage overlapping a maintenance outage. Okay, so I go back again to this circuit just to tell you what is happening here. Suppose we use this diagram. Suppose I want to maintain this feeder 1. I'm maintaining this feeder 1 according to the maintenance numbers that we just saw, and then suddenly this component goes out. While I am maintaining component 1, component 2 fails. So this is what we call a permanent outage being overlapped by a maintenance outage, right? So that is why we call it lambda PM, UPM, RPM, yeah? Permanent and maintenance outages overlapping. They don't occur at the same time. Yeah, it doesn't make sense. Otherwise, we will never maintain them. If by that action alone, we find that the load point gets lost or doesn't get the power. So come back to that equation, yeah. So lambda PM, RPM, UPM are the outage rate, duration and annual outage time of the load point due to forced outage overlapping a maintenance outage. Yeah, that's why it's PM. Forced outage overlapping a maintenance outage, not the other way around. Not the other way around. It cannot be MP, right? It has to be that you were maintaining something and then a permanent outage happened, rather than a permanent outage has already happened and you're also trying to maintain. I hope you are with me, right? Yeah, that's disastrous. So it will not be the other way around. So for two components in parallel or a second order failure event, minimal cut set, lambda PM, and I explained this sometime back when we were talking about the minimal cut sets, not sure if you remember. Component 1 is out due to maintenance. Component 1, lambda 1 double prime, please note. Yeah, I mean, I'm trying to tell you how to get these equations. Lambda 1 double prime, component 1 is on maintenance, and when component 1 is on maintenance, component 2 fails during the maintenance time of component 1. Clear? Then obviously the other outage is also possible, right? Component 2 is on maintenance, and during that component 1 fails during the maintenance time of. Clear? Same thing of course can be extended to 3 components in parallel, right? So using those equations which we have also seen before, yeah, and for 3 components in parallel, yeah, there are also equations. I remember having explained to you the other day this one as well. It's the same argument. Component 1 on maintenance, and then component 2 fails during the maintenance time of component 1, and while component 2 has failed, component 3 also fails during the overlapping time of maintenance and forced outage of component 2. So you can easily extend this analysis, and I've given you all the equations, you don't need to worry too much. Now, we know that we have lambda PM. We also have lambda PP. Remember I told you? Permanent outage overlapping a permanent outage. That means 2 forced outages. Component 1 is out, and then while you are trying to repair component 1, component 2 also fails. That's lambda PP. This is lambda PM. So if we want to look at the holistic evaluation of reliability, we must say that lambda overall is lambda PP plus lambda PM. And if I have transient failures, I'll have lambda PT, lambda permanent overlapping transient. And there is another thing that I wish I had more time, weather related failures. Due to adverse weather, we can have failures. So that is another factor that we can consider in a more detailed study. So this is it. I have shown you the numerical example. The same example, assume that each component is individually removed for maintenance once a year. Once a year means lambda double prime is, what is lambda double prime? Once a year, what's the number? 1 maintenance outage per year. So lambda double prime is 1. And the maintenance time is 8 hours, okay? I've just assumed those numbers. Lambda double prime is 1, R double prime is 8, okay? And then we do all these calculations. Lambda PM, 1 and 2 are overlapping, right? So permanent is 1 and maintenance is 2, and permanent is 1, maintenance is 4, and so on and so forth. So you can calculate the lambda, you can calculate the U, you can calculate the R. And then if you take the PP, the ones that we did earlier, you can get those numbers from the previous table, and then you can add them up. These are the total load point indices. This is the total failure rate, this is the total annual outage time, and this is the average outage time. Not very hard, it can be done, particularly for simple systems. It can be easily done using hand calculations. So I just thought last night I should share with you some examples of maintenance and ring system, meshed system, rather than just stay with radial. Don't want you to go away with the impression that everything is radial. Certainly not, okay? I think this is it, if I'm not wrong. Yeah. So I apologize again for the extended lecture and for delaying your tea break, coming between you and tea, and more importantly, between you and the exam. Okay? Thank you again for lending me your ears, and all the best for the exam. Okay?
1 week long course of GIAN. We all had 10 learning from basics to advanced level of reliability. So we look forward to being in touch with you. So thank you so much, sir, for taking this.
Thank you. I'm going to see you later, right? There is a valedictory. You can't get rid of me so soon.
So we'll have a quick tea break, sir. Everyone is requested to proceed to the machine lab, ground floor, 11 and main department. And after that, we'll have a written test in the same lab for about half an hour. Yes, Professor Uma Nangia ma'am, coordinator of this course, to address the gathering.
Very good afternoon to all of you. Foreign expert Professor Lalit Goel, Professor Nanyang Technological University, Singapore, Head of the Department Professor Rachna Garg, faculty members, dear participants, ladies and gentlemen. I welcome you all to the valedictory function of GIAN course on role of reliability evaluation in power system planning, operation and maintenance. As you all know that this was being held it started on 3rd March and it was being held till today morning, and you had appeared for the test also. And in this course, all the lectures were engaged by our foreign expert Professor Lalit Goel sir, who enlightened us about reliability and its applications to various fields, started with the introduction, probability and some engineering processes, and then to the power systems. We received overwhelming response for this course. 75 students registered, and I saw that this hall was always full with the participants. So this was how he made all the lectures very interesting and interactive, that people from academia as well as industry wanted to listen to him. And I'm sure the participants would have been fully benefited from his lectures, and they wanted to hear more of his lectures. Always there was a request that we would complete this lecture before having tea or lunch. And I am sure that those participants who are already into research work will use reliability as a tool in their research work for some, because they have the idea about reliability evaluation. And those who have yet to start the research work can choose this as one of the topics, reliability evaluation of power systems, for their research work. And I hope you enjoyed it all. And in addition to this, tutorial sessions were held by our own faculty, Professor Mukhtiar Singh and Dr. Prem Prakash. I think those tutorials made the concepts very clear which were discussed in the morning. Theoretical concept was discussed in the morning and it was presented as a case studies in the evening. And in addition to that, Dr. Monica also conducted this hands-on training on ANSYS software and ARK in association with ARK Solutions. And I hope you must have been fully benefited and you enjoyed your participation in this course. I wish you a happy future. Okay.
Thank you so much, ma'am. Feedback collection and implementation lead to a more effective and engaging learning experience. It improves course quality, enhances learning experience, boosts student satisfaction, supports institutional development, and encourages constructive communication. Now, may I request the participants to come forward and share their views about the course? Anyone from the participants, if willing to talk about the course experience throughout the week, are welcome to share their experience, please.
First day she was telling me she couldn't blink her eyes.
इतना अच्छा कोर्स हुआ है, आप लोगों के फीडबैक से ही एनकरेजमेंट मिलता है और तो आप लोग ज़रूर अपना फीडबैक दीजिएगा.
First of all, I thank to sir. He has delivered a tremendous lecture. Even I couldn't blink my eyes during all the sessions, and I learned so lots. Although this is not my field, but still I am getting so much engaged that I couldn't blink my eye. That's it. All the facilities are very good. Were very good. Sorry, and. I hope all the participants are benefited with the sessions like me, and I really hope in future we will meet up and interact in these sessions. Thank you.
Thank you, ma'am. Anyone else from the participants, if willing to share his or her views from the industries? Yes.
Bouquets, come on.
Please, sir. Please, sir.
Good afternoon all. Respected our foreign lecturer, sir, respected madam, HOD madam, Umanage madam, and respected to all. I don't know, I'm working in a distribution system at All India Institute of Medical Science as a tech maintenance engineer, as a junior engineer electrical. But I just took the course from sir reliability. I don't know I have any component have some reliability. But by taking the course, my mind has some reliability. When there is a fault in a system, we just replace it. But there is a system, their components have some reliability. I know after taking this course, I am highly privileged to the sir by coming and give us this some knowledge about reliability, which also linked to our revenue product. But always we change this some product, but we should know about the reliability of the system. I am highly appreciable and highly getting some knowledge from this sir. Thank you, sir. Thank you.
Thank you, sir. Anyone else from the participants, if willing to share his or her views? From other universities, from DTU, from industries?
आप लोग आइए.
Yes, sir, from Delhi Transco Limited. Please, sir, share your views.
नमस्कार सर, मेरा थोड़ा गला खराब है. मेरा नाम धर्मेंद्र सिंह है, मैं दिल्ली ट्रांसको से हूँ. सर काफ़ी इन्फॉर्मेटिव रहा है, काफ़ी कुछ सीखने को मिला है. कुछ कॉन्सेप्ट्स है जो मैं पहले अवेयर नहीं था. रिलायबिलिटी एक उसमें से पहला कॉन्सेप्ट है, बिल्कुल भी आइडिया नहीं था, बट काफ़ी कुछ सीखने को मिला है सर. उम्मीद है आगे भी कुछ इसको प्रैक्टिकली फील्ड में इम्प्लीमेंट कर पाऊँगा और कुछ गेन कर पाएंगे. चलिए सर, थैंक यू.
So, thank you everyone for all your active participation in this course. Now, may I request Professor Madhusudan Singh, local coordinator of GIAN, to share his views about this.
मैंने तो सबसे कम अटेंड किया. Very good afternoon to all of you, the dignitaries on the dais, the speaker for this GIAN course, Professor Lalit Goyal Saab, my colleague Professor Rachna Garg, Professor Uma Nagia, the coordinator, Professor Rizwan, I think he is busy somewhere, and participants, ladies and gentlemen. We have come to the end of this program, and today I got some time, so try to see what is going on. I was really impressed the way Professor Lalit Goyal teaches, and I hope that during 5 days you had ample opportunity to learn reliability, especially in respect of power system. Though in the beginning he told you that it is something which is very universal tool. Reliability is not limited to power system only, but yes, specific to power system he did a lot, and lot of techniques I hope you learned. And some of you, especially those who have come from utilities, industries, they can think how these tools they can explore for their routine operation and maintenance work. I was just talking to Professor Rachna that we can have a joint project with the help of Transco, where Transco can just provide the data on some feeder section, and our students here can apply these tools. Those mathematical part they can very well do, and that way some information, some solutions we can suggest to Transco also, and at the same time our students will able to complete their project work and all. So that's one way we will explore and try to connect with you. We are really grateful that Professor Goel agreed to our request. He spent almost 5-6 days totally dedicated for this purpose, and we would like to continue this effort, sir, in near future also. We will be in touch with you, and maybe we organize a similar kind of activities, little advanced level, and those who have learned these topics may participate again. So this way, I once again thank especially Professor Lalit Goel coming all the way from Singapore and helping all of us to learn this new topic. I am also thankful to Professor Rachna for helping in organizing this program, and especially the coordinator, Professor Uma Nagia and Professor Rijwan, who had worked a lot for organizing the logistic of these programs. So with this, I hope that all participants enjoyed these important moments. You all have something to carry with you, and I thank you all for participating in this program. So I think we have some memento from the university to Professor Lalit Goel. Has it come or not? Office वालों ने भेजा था office? Hopefully it is on the way. Will hasn't finished. अच्छा ठीक है, तो that you know. ठीक है. With this, I once again thank you all. Thank you very much.
Thank you so much, sir. Now may I request Professor Lalit Goel, sir, to share his views about this esteemed gathering. Thank you.
Thank you very much, Monica. Yeah, doesn't matter, they're not looking there. They're looking at us. Okay. Well, good afternoon, everyone, for the last time. Yeah, you're not gonna hear my good morning, good. I don't think we spent a lot of time in the afternoon, but still. Honestly, it has been an honor and privilege for me to be here at the invitation of DTU and through the GIAN initiative. And I have enjoyed the last 5 days, truly. I hope that you have enjoyed as much, if not more, but the main thing is that you need to be a little bit more passionate about what you do. Need not be in reliability. You have to have some passion. When I came to Singapore in the year 1991 from Canada, I may have told you this story 5 days ago, but I didn't go because I wanted to. I went because my better half didn't want to live in Canada because it was very cold, minus 40 degrees and so on and so forth. So I was a reluctant teacher. I didn't want to be a teacher. And yet, when I was teaching the first class of mechanical engineering students, 450 students in the class, within 10 minutes, I realized that they were listening. So this is how the journey started, and the rest, as they say, is history. I have enjoyed teaching so much. I mean, I can't believe it, that, at that time, I didn't want to teach. It was like sometimes you do not know your calling. Yeah, you just don't know when that calling will arrive. Be prepared for it. Have a passion. Do everything with passion. To those researchers and young faculty, I think you should aspire not just to publish well, but also to teach well. These days, research goes hand in hand with teaching. In our own university, we've got a 12-point scale, 5 for research, 5 for teaching, 2 for professional services. So the message from the management is clear. Teaching and research have equal weightage. Yeah. Sometimes, people still say, hey, this is just on paper. Actually, they just look at research, but that's not true, because I'm also part of the management in some ways. And when we make decisions, I know that if somebody is a bad teacher, he will not get promoted, he or she. So it has a value. So get your passion. If you are a teacher, if you are a lecturer, if you are a faculty, do not put teaching under the carpet. It should actually be your first priority. Because if you are so good and passionate about teaching, you will also do very well in research. At least that's the mantra I believe in. And for the young researchers and faculty, I also hope that some of you, sooner rather than later, will also aspire to become IEEE fellows, IET fellows, and so on. It doesn't happen overnight. You really have to work hard, and you have to improve upon your networking. So go and attend conferences worldwide, not just within India. Where possible, go and attend major conferences, and that will increase your circle. And when you come to that stage, people will be willing to write references for you. And that's the day that you should look forward to in your entire journey. So once again, I'd like to thank DTU. Professor Uma Nangia has been working tirelessly. I'm sure she'll sleep well tonight. I have been bothering her for the last few months, and now today she's going to say good riddance. Yeah. And of course, Professor Madhusudan Singh, who's the GIAN coordinator, and Professor Rachna, their support has been instrumental, if I may say, in the successful run of this course. I mean, I should not be saying whether it was successful, but as I enjoyed it, and the look on your faces told me that majority of you were enjoying it. So maybe I was wrong, but I hope not. Okay. Now, again, just like this morning, I was keeping you from, I was coming in between you and tea, right? So right now, I suppose there is a tea session after this. So again, I'm coming in between you and tea. So I'm gonna stop talking now. Wish you all the very best in life. Okay. Take care. If there is anything I can do for you, you have my email on the first slide of your notes. Feel free to write to me. I have my own rule when I tell students, and you are my students, that I will respond promptly and no more than 24 hours unless I'm on a long flight. Thank you.
Thank you so much, sir. Now may I request all the dignitaries to come forward for certificate distribution. Let them come. Manju Sharma. Go. अच्छा अच्छा. Okay okay. We'll start within 1 minute. 1 minute, ma'am. Just 1 minute. Wait. क्या हो गया? जनगण मन कहाँ से आया? Okay, shall we start? Okay. So, Miss Manju Sharma.
कैसे नाम है नाम
Miss Shalini Sharma. Mr. Kuldeep. Mr. Kuldeep, Mr. Dharmendra Kumar Singh, Mr. Tushar Patil, Mr. Himanshu Raj, Miss Rekha, Mr. Ashutosh, Dr. Devinder Kumar, Mr. Udit Mittal, Mr. Saurabh, Dr. Shikha Gupta, Miss Ruchi Gautam, so we can have claps for all the participants who are getting the certificate. They spared their time to attend this course. Mr. Sarat Kumar Rana, Mr. Abhishek Kumar Gupta, Miss Anupama, Mr. Ganesh Kumar Jaiswal, Miss Urmila, Miss Rehma, Dr. Priyanka Anand, Apurva, Shefali, Mohammad Mudassir Masoom, Mr. Deepak Kumar, Miss Arpana Singh, Shubham Goyal, Anuj Kumar, Miss Poonam, Mr. Gaurav Yadav, ठीक है अरे मेरा रख दो। अरे दो ना, अरे नहीं नहीं हो गया, अरे हो गया ना, अरे Okay, the participants who were not present here can get the certificate after the session. Thank you all the dignitaries. Yes, ma'am. अरे नहीं,
Miss Monica, Miss Poonam,
Okay, sir. Yes, ma'am. Thank you all the dignitaries. Mr. Puneet Kumar Dikshit. Okay. Dr. Naresh Kumar. Mr. Khalid. I think. So that's all. So all the participants present here must have got the certificate, right? Okay, thank you all the dignitaries. Now, in recognition of the exceptional contributions of coordinators, working team and devoted volunteers, I now invite Dr. Ashish Kulkarni to propose the vote of thanks.
तुमने कर तो दिया, मैंने कहीं ऊपर बैठने वाले होंगे
Ma'am, I'll invite. Okay. Okay. Yes, ma'am. We'll continue the session. Everyone, please be seated. Now, I invite Honorable our head of the department, head of the electrical engineering department, Professor Rachna Garg, to share her views about the course and interaction with Professor Lalit Goyal.
A very good afternoon to all of you. Our foreign expert, Professor Lalit Goyal ji, local GIAN coordinator, Professor Madhusudan sir, who is also the registrar of the university, organizers of the course, coordinator Professor Uma Nangia, and faculty members and volunteers and all the participants who are present here. At the outset, I would like to thank each and every one of you for making this program a success. First of all, I would like to say that I had also attended for a few times the lecture of Professor Lalit Goyal, and I am really impressed the way he has delivered his lectures. And today again, I was listening to his lectures in live mode. I was in the department. I was not able to come here, but I was listening to it on in live mode. And his way of delivery and the way he explained things was really very good, sir. We also have to learn a lot from you. And I hope participants must have learned about reliability, because reliability is not a very, you can say, easy concept also, and it is not very popular also, because it is not one of the regular courses. Normally it is run as electives in most of the university, so only few of us has studied actually what reliability is and about reliability. So this course is very, I think, useful to all of us, because whenever we are talking about any system, any component, reliability is the first factor which we have to consider. And this is the last thing that we consider. So with this lecture, with this GIAN course, all of you must have realized the importance of reliability, and in some way of or other you will use it in your research work, or you may take up your research work in the area of reliability. There is lot of opportunities in the field of reliability. But yes, it is very mathematical in nature, and this mathematical subject sir has made so interesting. So I really want to give him a very big round of applause to Professor Lalit Goyal. Also, I would like to thank our local GIAN coordinator, Professor Madhusudan sir, and the coordinator of the course, Professor Uma Nangia. If they are not there, this course would not be possible. Their efforts has made it possible for us to attain this course, to interact with Professor Lalit Goyal. So a very big thank you to the local GIAN coordinator and the coordinator of this course. Last but not the least, it is the participants who make a program success. I hope all of you must have learned a lot from this GIAN course, and also from electrical department of DTU. In my first, when the course started, I requested the outside participants to go around the laboratories in electrical engineering department. I hope you must have visited the labs and must have seen something which you can imitate in your universities, in your colleges also. And also I would like to say that if this GIAN course is over, is still, if any of you wants any support or any help from electrical engineering department, we are always there to help and support you. It is not that with GIAN our relations are over. It is now for lifelong. And whenever we organize any other course, we will inform you, and you can come if to attend those courses also. I would also like to thank our dedicated volunteers, Monica, Anupma, and all other volunteers, Ganesh, who are working tirelessly for making this program a success. Thank you. Thank you.
Thank you so much, ma'am. Now, may I request Professor Madhusudan Singh, Professor Uma Nangia, Professor Rachna Garg, ma'am, Dr. Ashish Kulkarni sir, to present a memento as a token of regard to Professor Lalit Goyal sir. Thank you, sir. Thank you, ma'am. Thank you, everyone. Now, I invite Dr. Ashish Kulkarni sir to propose the vote of thanks.
बोल ही चुके हैं सर आप सर बचा हुआ बहुत बड़ा है ना।
हाँ, एक बहुत बड़ी चीज बची हुई है जिसको मैंने थैंक्स
नहीं बोला आपने। फॉर्मेलिटी के तौर पे जो है फाइनल वोट ऑफ थैंक्स, वैसे मल्टीपल हो चुके, बट अगेन वन फॉर्मल फाइनल। As this GIAN course comes to an end, we, the Department of Electrical Engineering, would like to thank all those people who have directly or indirectly helped us in conduction of this course. First and foremost, we would like to thank our Honorable Vice Chancellor, Professor Pratik Sharma, for providing all the support and financial assistance and other things which are required to conduct the course. Secondly, we would like to thank our registrar and the GIAN coordinator, Professor Madhusudan Singh, for providing all the logistical help and doing all the administrative work behind the scenes so that this course is approved and we are able to conduct this course. Next, we would like to thank the DTU administration for providing all-round logistical support to conduct this course. Then I would like to thank the PRO and the videography team, which has painstakingly taken efforts to record all this event and stream it live on various platforms. Then the main person of this course, the foreign faculty, Professor Lalit Goyal, for coming all the way from Singapore and conducting this course and spending this time and his experience with us, sharing all the experience and knowledge that he has gathered over the years. We are lucky that the Government of India has given us a platform like GIAN, where we can bring in foreign experts and get the knowledge in-house delivered to us. So thank you, Government of India as well. Then I would like to thank the course coordinator, Professor Uma Nangia, and the co-coordinator, Professor Rizwan, who have taken all the efforts to conduct this course and do all the works on the forefront. Any course to be conducted of this magnitude, you require a team of dedicated volunteers. So all the PhD scholars who are working as the volunteers over here, Dr. Monica, अपनी डॉक्टर तो एक ही है यहाँ पर, हाँ, बाकी तो और होने वाले हैं सारे, अर्पणा है, गणेश है, और कौन कौन है, बहुत सारे नाम है ना, रायमा है, अभी मेरा व्हाट्सएप खुल नहीं रहा तो नाम मेरे पास है नहीं हाँ, आगे नाम आगे सर, ठीक है, शेफाली, दीपक, गणेश एंड अपूर्वा, और इनके अलावा और भी कोई वॉलंटियर्स है, so big hand to them. And then there is faculty and staff of Electrical Engineering Department for gracing the occasion as well as attending the program as and when possible. And last but the most important people, the participants who have come all the way from various places to attend this course. A big thank you to you. And हाँ सर, वो भी करता हूँ, दो है, अब मुझे आके देखना पड़ेगा नाम कौन है because I am a stand-in person, I am not the right person to give the vote of thanks. Yeah, our sponsors KNB and Nasroz, they have given a wholehearted support to conduct this program. And apart from this, any person or any helping hand directly or indirectly which I don't know, a big thank you to all of them, and thank you to all of you.
Now I invite all the esteemed guests, faculties, participants to join us for the group photograph.
यहीं खड़े रहो।